I'm Ahmed Daud, and in this session, we will continue our discussion that we have started in the last session on the hyperparameters of decision tree. So now we will discuss max feature. So max feature is again one of the hyperparameter, but it does not control the growth of the decision tree. Okay, so how it will work? At each particular node, if you specify some value to max feature at each particular node, it will consider that number of features for the split purpose. Okay, so I will give you an example. Then let's say if you have specified here max feature is equal to 4. Okay, so if you specified max feature is equal to 4, and you have this data set that you can see here, this data set which have a b c d e f g h, total 8 number of features, independent variables, and you have one target variable. Okay, now at each split, at each node, when you are going to split, you if you have mentioned here 4, you will randomly select 4 features from this. Let's say you randomly select b at this particular let's say at this particular node. You want to do splitting and you want to create this type of leaves. So you consider you will extract some 4 random features from it. Let's say you randomly select b, c, e, and h. Okay, so b, c, e, and f, you have considered these 4 features. Now you at this position you will extract a split value or decision rule from these 4 features only. You will not consider other features like a, d, f, g. Okay, you will consider just these 4 features at this position. So at each node, starting from the node root node, when you are going to do splitting, you will select randomly 4 features, and then you will perform you will extract your best split value. If you have mentioned splitter is equal to best, then you will try to find, or your algorithm will find best split value out of all split values of the randomly features that you have extracted. Okay, at each particular node, at each node where you are going to do splitting. Okay, and if you have mentioned a splitter is equal to random, and let's say you are doing splitting at this position. Okay, so you are doing splitting at this position, you have randomly find out your algorithm randomly extracted 4 features, because you have mentioned max feature value is equal to 4. So let's say a, c, f, h, you have extracted these 4 features. What it will do, if you have max feature here, max features equal to 4, and splitter value is equal to random. Okay, is equal to random. So what you will do here, here these are the 4 features, and this is the target column. Okay, this is the target column. So you will randomly select the one of the split value between the mean and max value of a, and then the randomly select one split value between the mean max of c, then for f, then for h. Then you will select one of the best split value out of these 4 random split values. Let's say you have selected this split value of the c feature, and you have selected the split value, let's say 3.2. So you have extracted this decision rule for this particular node. Okay, so very simple, you have to consider just that mentioned number of features, or your algorithm have to consider mentioned number of features at each node when it going to perform the splitting. Okay, so there is mentioned values here like a square root, log, base 2, auto, and you can also pass, like here if you will pass auto, it will consider as a square root of the features, and if you will pass square root, it will again consider as a square root of features. Let's say you have 8 features, then the square root of 8 will be some value, and 2 point something, but it will consider as 2 integer. Okay, and in the case of log 2, if you will pass here the log 2 to this max feature, it will take a log 2 of total number of features, like total number of features are 8, so log base 2 of 8 will be 3. So it will consider 3 features randomly at each split or at each node for the splitting purpose. Okay, so if you will pass and no value any of them, then default is none, and it will consider all the features, all 8 features at each node. Okay, so here if you can also pass some fraction. Let's say if you will pass here, your total number of features are 8, and you will pass some fraction, let's say 0. Let's say 4. Okay, you will pass 0.4. What it will do, it will multiply with the total number of features, it will be generate 3.2. Okay, so it will take a max between 1 comma int 3.2. It means int is just taking the extracting the integer from it, so it means 1 or 3, it has to select max of both of them, so it will select 3. Okay, so if you will pass 0.4 and your total number of features 8, it will consider 3 number of features at each node. Okay, and this condition, or you can say this expression, they have mentioned here to avoid the feature, like if you can say multiply after multiplication there will be 0.7, then it should not be considered, then it will consider at least one feature. Okay, but here keep in mind there is a note that the search for split does not stop until at least one valid partition of the node sample is found. If it requires to effectively inspect, it can inspect more than the max feature that you have mentioned. Okay, if let's say you have extracted the 4 features from let's say a let's say you have extracted 4a B, C have 4 features at some node, and all of have like A have just 0 values, B have just 2 values, and C have all the values 3, and F have all the values 4. It means there is no valid partition in these 4 features. So it can consider more than 4 features if there is no valid partition. To do some partitions, okay, to get some valid partition rule. Okay, so random state is again a hyperparameter, and you have seen this random state hyperparameter in a lot of modules that when we are using. So it controls the randomness of the estimator, the features, like if, randomly extracting the features. So for that purpose it can be used. So features are always randomly promoted at each split, they are saying, even if you have mentioned splitter is equal to best, because if you have mentioned splitter is equal to best, best does not mean that you are extracting best features. Best is further process when you have selected your uh, when you have randomly select your let's say 4 features. If you have mentioned max feature is equal to 4 at some node, then the further process is of splitter. If the splitter value is equal to best, then it will try to find best split value present in the 4 features. Okay, so there is another important point to note here. When max features less than number of features, like say you have max feature 4 and number of features are 8, the algorithm will select max feature at random at each node before finding the best split among them, that I have told you. But the best found split, okay, so they are saying that found split may vary across different runs. The reason is that even if you have mentioned max features is equal to 8, okay, if your total features are 8 and you have mentioned max feature is equal to 8, then again there is a chance that your best found split or your split value or your decision rule can be different if you run at this PC and if you run at another PC, and if you have used let's say you have closed your Jupyter notebook and again you have opened your notebook, then there can be a chance that you will get a different type of tea. The reason is that if let's say uh, uh, you have selected you have 8 max features equal to 8, and at each node you have to consider all the features. Now you have to find best split value out of all. So let's say there are 4 best split values that have same value. These split values have a lower Gini priority compared to our other split values, but they are same exact to each other. Then this algorithm will consider randomly one of them split value uh, at a node. Okay, so here they also have mentioned that is the case if improvement of the criterion is identical for several splits at some node, then one split has to be selected at random. Okay. And always it is a good practice to pass some value to random state. The reason is that they also mentioned to obtain a deterministic behavior during fitting, random state has to be fixed to some integer value. Okay, so if you will pass some random state any value, let's say if you will pass random state value is equal to 4. So whenever you will pass a random state is equal to 4 and pass the all the same values, then you can get the same type of decision tree. Okay, so to get the same type of randomness, we usually pass this value. It actually means the same. If you have a decision tree and you are running your Jupyter notebook and you have closed your Jupyter notebook, again if you will run your Jupyter notebook, if you want to get the same decision tree that you are having previously, then you should specify some value to random state. Okay, and let's say previously you have specified random state value is equal to 4, and again if you will specify random state value is equal to 4, then it can give you a same tree that you are having previously. But if you have not specified some value to a random state previously, and now you have all the hyperparameter values same, all the data same, everything is same, but you have not specified any random state value previously, then again you will when you will run again your Jupyter notebook, you will open Jupyter notebook, run the program, then may be chance that you will get a different type of decision tree. Now there is another hyperparameter which is max leaf node. It also controls the growth of the decision tree. It means it actually tells that or restrict the growth of the tree. In that way, it say that I want just this number of leaf nodes. Okay, let's say if you will mention the max leaf node equal to 3, then it will whenever your tree will get 3 leaf nodes, it will stop there. Okay, but it will get a 3 leaf node in best first fashion. Okay, best nodes are defined as relative reduction in impurity. Okay, the nodes that let's say you are reached at this position and your max leaf node is equal to 4. Now you have to produce 4 leaves, your algorithm has to produce. You can split at this position, at this position, at this position. So you will consider which if you split at this position, how much the decrease in impurity. If you split at this position, how much the decrease in impurity. If you split at this position, how much the decrease in impurity. Which split is giving the more decrease in impurity, you will consider that. Let's say out of these three nodes, out of these three nodes, the splitting of that node is giving you the maximum reduction in impurity, then you will consider that splitting and you have created here 4 leaves. Okay, again if your max leaf is equal to 5, then again you have to consider these 4 leaves and which leaf node will give you the or which node can give you maximum reduction in impurity, you will consider that. Okay, so that's why they have said that it work in the best first fashion. Best nodes are defined as the relative reduction in impurity. Okay, so if I can show you here an example of max leaf node. If you specify a value to max leaf node, it will create a tree that have that exactly that number of tree. Okay, because you are saying that I can bear maximum number of these leaves. Okay, maybe it can give you, if your tree is can be restricted due to some other parameters, you can get less number of leaves, but you will not get greater than that number of tree that you have mentioned here. Like here I have mentioned maximum leaf nodes is equal to 6, so this tree has produces 1, 2, 3, 4, 5 and 6 leaf nodes. Okay, so there is a chance that it can depend upon the other aspects, that you can get less than 6, but you cannot you will not get greater than 6 leaf nodes if you specify here 6. Okay, because here the condition is maximum leaf nodes. Okay, so next important hyperparameter is minimum impurity decrease. You can also specify that this amount of impurity, if decrease when you will split that node, then you should consider algorithm should consider this splitting. Okay, let's say if this algorithm reach at this position at this node. Now it has to split this node further into some childs. If this node can produce the decrease in impurity as mentioned here, or greater than this value, then this splitting will be allowed, otherwise it will not allow. I can give you here an example. Okay, you will get more precise idea. Okay, so let's say at this particular position, at this particular node there is a Gini impurity 0.5. Okay, and when you will split this node, now your child nodes have this gene impurity. Okay, 0.214 gene impurity your left child have, and the right child have 0.059. Okay, if you will do a weighted sum of these childs, you can get the impurity after splitting this node. Okay, so this is a 0.5 your parent. This is at that particular time, this is a parent node, and this is you can say gene impurity of your left child, and this is the gene impurity of your right child. You are multiplying with the fraction with the weight, like this right child have 33 samples out of 74, and this left child have 41 out of 74. So when you will calculate this one, this is saying that 0.15. So now your impurity decrease from 0.5 to 0.15. Okay, but this is just for the case of this particular node. This particular node of the impurity of this particular node is decreased from 0.5 to 0.15. But if you will consider whole number of points, which are 105 points. Okay, if you consider the whole reduction in the impurity of whole data set, then you have to again multiply with the number of points that at this particular node, divided by the number of total points, because you want to see how much the total reduction, how much the reduction in impurity in total number of points. Okay, so this 0.5, this is the reduction of the impurity. 0.5 minus 0.15, it is for this case, just for this case. Okay, if I will make it right, just for this case. Okay, now it will say that how much the reduction in impurity in the whole data points this splitting has produced. Okay, you will multiply again the reduction in impurity with this number of points that at this particular position by divided by the total number of points, which is 105, and that you can see from your root node. Okay, now you have find out the value 0.25. Okay, so there is total reduction in impurity this split has produced is 0.25. Okay, now if your mean impurity decrease value you have specify here 0 point let's say 26. Okay, so you are saying that splitting will be allowed if minimum impurity decrease is 0.26, but here the impurity decrease is 25, then this splitting will not be allowed. If this will be a 0.25 or less than 2 or you can say 0.25 you have mentioned here, or then this splitting will be allowed because you have passed the condition or passed the value that you have specified this hyperparameter, which is minimum impurity decrease. Here your minimum impurity decrease, here your impurity decrease 0.25, which is meeting with your minimum condition, then this split will be allowed. Okay, you are saying that minimum impurity decrease should be uh, the impurity decrease when you do splitting should be greater or equal to this value that you will pass to this hyperparameter. Okay, now keep in mind this hyperparameter, if when you have passed your data set and during training part, during fit method, you have also passed your sample weights, like I have discussed in the previous case. There is some cases when you can pass the sample weight if you have sample weight in along with your data set, like in the mean weight fraction also can consider the sample weights. If you have specified your sample weight, during the training part, if you also passed along your data set, your sample weights, your list of sample weights, then instead of just calculating the, you can say, calculating the sum of the samples, it will calculate the sum of the weight of the samples. Like this is the 74 samples that were present at that node. Okay, and 105 samples are at the root node, total number of samples. Okay, there are 74 samples, and on the left child there were 41 samples, and on the right child there were 33 samples. Okay, this is exactly the same. If you will see the number of samples at the node where you are going to separate, which is 74 here. Here the number of total samples 105. Here the number of at the right child samples will be here 33. This is again 74, and this is again 41, and this is 74. Okay, but if you have passed sample weights during the training part, then it will not consider the sum of the samples, it will consider the weighted sum. Okay, and you know, weighted sum is the sum of the weights of the samples that are belonging to the sample. Here n will be the sum of the weights of the total number of samples, and t will be number of the sum of the weights of the samples that are present at that particular node. This is the sum of the weights of the samples that are present at the right node, and the sum of the weights of the samples at the left node. Then again the formula is same, formula will be same. Okay, impurity of the node minus the weighted sum of the impurity of your child's, and then multiply with the fraction of that weight, that node in the whole data set. Okay, so this like here you I have mentioned previously, in the mean weight fraction leaf, if you will pass the weight, sample weights during the training part, it will also consider that. If you will not pass the sample weights during the training part, and you have specify here a mean weight fraction leaf value 0.3 during as a hyperparameter value you have specified, then it will consider that your all sample has equal weight, let's say one weight. Okay, but the process will remain same. Okay, so now the class weight. It is one of the important hyperparameter. It actually not control the growth of the tree. It is for the different purpose. And I have also given you the quite deep understanding of class weight hyperparameter in the logistic regression class, when we were discussing logistic regression hyperparameters. So you can pass here the list of dictionary, and you can also pass that this string value balanced, and if you will not pass any value, this will be remain none. Okay, so weights, here you are saying that class weight. So let's say you are going to solve the classification problem, and let's say you have two classes, then you can specify the weight of each class. If you will not specify the weight of each class, then all classes will be considered have same weight. Okay. Okay, so you can also specify as there is this relate to the target variable. So you can also pass the weights for the multi-output problems, that till now we have not done any multi-output problem. Multi-output problems are the problems in which your output can be multiple values. Okay, usually we were having output just one value. Okay, one class one value, in classification one class. Okay, multi-output problems in which your target column can be more than one. Okay, till now we have not considered or have not done any example regarding multi-output, so I will remain that part as it is. Okay, so here you know, if you will pass the values for your classes, you can pass here in the form of a dictionary, but if you will pass the balanced list, then you balanced string, then it will do the same way like I have given you the understanding in the logistic regression class. So I will give you a quick recap, but here you can see for a while balanced mode uses the value of y, which is your target column, to automatically adjust weights inversely proportional to the class frequencies in the input data with using that particular formulation. N number of samples divided by number of classes into np.bin count y. Okay, for a while we can consider that one also. Okay, let's say you have this data set. I am copying that exactly the same example that I have given you in the logistic regression classes, hyperparameter class, so that you can get a quick recap. Okay, so if your data set have total number of 10 samples and you have 8 samples belonging to zero class and 2 samples belonging to one class, this one and this one. Okay, and if you will train your model on this type of data set, as you can see, this is very unbalanced data set. Now there are two options that when you will pass unbalanced data set, your model will be you will get a biased model which will have more percent chance that will predict the classes that have more number of samples when we have feeded. Okay, means that your model in which you will pass unbalanced data set, it will be more sure about the prediction of the zero class, or about the classification of zero class, and it will be less sure about the classification of one class because it has seen less number of samples during the training part belonging to one. Okay, so what we can do, there are multiple techniques, and the technique that is available here, it is that you can pass class weight is equal to balanced. Okay, what actually it can do, it actually here you have 8 number of samples belonging to zero class and 2 number of samples belonging to one class. It will decrease the weight of the samples. It will decrease the weight of the samples that have the output or a target value 0, but that have class 0, and it will increase the weight of the samples that have the class is equal to 1. Okay, that have their output value is equal to 1, so that it can balance your data set by tweaking the weights. Okay, originally all the samples have equal weight, and all the classes also have equal weight, but you can tweak, like here they have mentioned. If you will pass balanced value, what it will do, it will use that formulation, number of samples. Let's say in our example their number of samples are 10 divided by number of classes into np.bin count. Bin count in work in that way, at the 0th index your number of samples belonging to zero class, at the 1th index their number sample belonging to one class. So 8 comma 2. So here this will be 10 divided by 16 comma 4, and when you will solve you will have this one. You will get this type of array. It means that zero class, any sample belonging to zero class have weight 0.625, any sample belonging to one class have weight 2.5. Okay, now whenever you will multiply 2.5 with the, as your total number of samples are 2, so with belonging to one class your result will be 5, and your total number of samples belonging to zero class are 8. When you will multiply you will get again 5. So now automatically you have not tweaked your data set, but your data set becomes balanced on the basis of class weights. Okay, just you have given different weights to the classes depending upon their frequencies. Okay, to make the balanced data set, whenever you will pass the you have imbalanced data set and you have passed the value to this class weight as balance, it will automatically adjust the weights in that way that we have solved here, and then you will whatever model you are using, if you are using decision tree, you will get more like a balanced model, not some biased model, because you have balanced your dataset before feeding to your model. Okay, so and you can also specify here the value of class weight if you want to specify by yourself. Let's say by using, they are saying by using dictionary, you can pass here like they have given here the example. uh, if you are have a data set which have two classes, And you can also specify here like a zero class have two weight and one class have like a three weight. Okay, it means whenever each sample belonging to zero class have two weight and each sample belonging to one class has three weight. If you will pass that type of dictionary to that class weight value, it can update the weights, or it will give the weight uh, according to the mentioned values. Okay, so this class weight is not for the you can say to control the growth of the tree. This class weight is to make the to give some weights to the classes. Okay, now they have also given important note. If the weights like you have also specified the class weights and your sample when during the training part, you also have passed the sample weights. Okay, means sample weights associated to each sample, and class weights are the associated to each you can say each class. Okay, so what will be the total weight of the sample will be the multiply with the sample weight. Okay, let's say here I can give you an example here. Let's say uh, uh, I can give you here example in the like the problem that we have solved previously, like this one. Let's say here this target column have four samples and have classes 0, 1, 1 and 1. Okay, so if you will specify that your 0 class has two weight and your 1 class has let's say three weight like I mentioned previously. Okay, so what will happen, and your samples also have some weights. Okay, and these weights are also be referred to the samples that having this 0 class. So what will happen, this one weight of the sample weight will be multiplied with the weight of the class that is 0 class, so it will be multiplied with the 2. So 0.7 will be multiplied with the 3 because it belong to the uh, one class. 0.2 will be multiplied with the 3 and 2 will be multiplied with the 3. Now the weights of your you can say samples will be updated. Now this sample will have weight 2, this sample will have weight 2.1, this sample will have weight 0.6 and this sample will have weight 6. Okay, now you will have new weights. The reason is that you have sample weights, you also specified your sample weights during the training process, and you also have specified your class weights. So class weights actually means the same like the sample belonging to that class. Okay, now over total weight of each sample will be the multiplication of sample weight with the class weight. Okay, so I was telling you here like this is the important note. They have mentioned that if you also have specified your sample weight, then and you here are passing some values of class weight, means you are specifying your class weights also, then it will be multiplied with your sample weights. Okay, so this is about the hyperparameters. As I discussed that this complexity parameter we will discuss in the post pruning session, but for now we have discussed all of the hyperparameters. Now in the next session we will play with these hyperparameter values, or these hyperparameters actually, on the Jupyter notebook, and then you will get a more you can say good idea, but underlying concepts and structures of each hyperparameter, I hope you are clear till now.